Hello, this is Jack Jackson. We're going to prove the parallelogram theorem today. So by the way, if you are in a high school geometry class and you're only studying Euclidean geometry, you can ignore anything I say about other geometries here, but this will be a good video for you. Um, so in general, a quadrilateral ABCD with where one diagonal breaks it into two congruent triangles with a rotation, that is specifically ABC triangle, ABC, this triangle down here, is congruent to CDA, that triangle up here, by rotating around this point of intersection of the diagonals by 180 degrees. That is a class of quadrilaterals. A parallelogram, by definition, is a quadrilateral with both pair of opposite sides parallel. It turns out that in Euclidean geometry, these are exactly the same class of quadrilaterals. And when you're proving things about parallelograms, the key is to go by way of proving these two triangles are congruent depending on what you're given. If you're given that it's a parallelogram, we start with that. We have to find enough to make those two triangles congruent. If you're given some other set of conditions where you can show those two sets of triangles congruent, then we'll be able to show it's a parallelogram. Okay, at least in Euclidean geometry. So we're going to look at what properties we're going to prove all the cool, interesting properties that a parallelogram has. We talked about some of those in the previous video, but we're going to prove them in this formally in this video, and we're also going to prove many of the converses. So it turns out I've got this table here. Let's see here. Make this a little smaller. Almost see the whole table here. Okay, and we have a whole bunch of different conditions, conditions A through J. And it turns out that in Euclidean geometry, any one of these conditions is enough to put it in this class of quadrilaterals where we have these two triangles that are congruent by a rotation, which is also the same class of triangles as quadrilaterals as parallelograms. Okay. Now, when we're looking at some other geometries like hyperbolic and spherical geometry, it turns out that this class of quadrilaterals where the diagonal and the sides make these two triangles congruent, again with a rotation, that still gives you most of the properties that we would normally have in the class of parallelograms in Euclidean geometry. So every line of this table works both directions. If you have these congruent triangles, we can get the condition over here. If we have the condition over here, we can show they have the congruent triangles. So what that says is these conditions A through J, any one of those is enough to put us in this class of quadrilaterals that we call parallelograms. Now, if you look, this part in the middle documents which way the arrows go for all the different geometries. And again, for Euclidean, they all go both directions, but in hyperbolic and spherical, they may only go one direction or maybe neither direction. So first of all, there is no such thing as a parallelogram in spherical geometry, so you know it's not mentioned here. In hyperbolic geometry, the class of parallelograms is a larger class than the class that has these triangles congruent. But it turns out if the triangles are congruent in Euclidean or hyperbolic, we can prove that it's a parallelogram. Whereas we can take, if it's a parallelogram, we get these triangles congruent. That works in Euclidean, but not necessarily hyperbolic. So you see how the table kind of works that way? So we can go from A in Euclidean and hyperbolic to get one pair of opposite sides parallel and congruent. And in Euclidean, that's enough to go back to get the triangles congruent. Or if we have in all three geometries, Euclidean, hyperbolic, and spherical, we get two pair of opposite congruent sides if we have these triangles congruent. And if we have the two pair of opposite sides congruent in all three, we can get back to these triangles congruent. We can go back and forth um, for that one. The pair of consecutive angles are supplementary. That only works in Euclidean in both directions. In Euclidean, hyperbolic, and spherical, if you have the triangles congruent, you get two pair of opposite angles congruent. And in Euclidean, if the two pair of opposite angles are congruent, that makes these triangles congruent. In Euclidean, hyperbolic, and spherical, if you get these two triangles congruent, then it turns out that the diagonals bisect each other. And in all three, if the diagonals bisect each other, you can get these triangles congruent. Okay? And we have rotational symmetry about the intersection of the diagonals through an angle of pi radians, or 180 degrees. That's going to happen when you have this. And if you have that rotational symmetry, then you're going to get these triangles congruent. And all three geometries, if you get these two congruent, we get these little triangles, the two sets of little triangles congruent where we're using the midpoint as a vertex. And in all three geometries, if you slice it with one diagonal and you get these triangles congruent with the rotation, then it's also the same as if you erase that diagonal, draw the other diagonal, and get the two triangles congruent with a rotation. So we're going to prove this. And the key in every case is to somehow get to this set of congruent triangles. Okay, so let's just go through here. We've got conditions A through J. So for the first section of the proof, we're going to start by assuming property A, that we have quadrilateral ABCD with triangle ABC congruent to triangle CDA. Then we proceed to prove that this implies each of the properties B through J on the right side of the table above. Okay? So corresponding parts of congruent triangles are congruent. So once you get these two triangles congruent, now once again, it's A, B, C, that's the triangle down here, is congruent to the triangle up here. So AC is the part, the diagonal there that we're looking at. Okay, then the part that we're looking at up here, if it's A, B, C, to get them corresponding, it's C, D, A. Okay, that's what we have right here. Okay, anyway, you've got two triangles that are congruent, so all the corresponding sides are congruent. Of course, the diagonal is congruent to itself, but the thing that picks up for us is that these opposite sides have to be congruent, which was D. So now we have condition A implies condition D. Now we also have some corresponding congruent angles. Angle B, that is CBA, is congruent to angle ADC, so we have a pair of opposite congruent angles. We also have some other angles that are congruent. Let's see, BAC is congruent to DCA, this one up here, and this one, let's see, yeah, this one right here, the little one at A, and this little one up here at C. And then we also have a corresponding one here. ACB is congruent to CAD, right? So this angle up here is congruent to the one here. Okay? Now, let's do the other diagonal and forget this diagonal here. Well, we've already established that we have opposite sides congruent. And if this diagonal is going there, it's going to be congruent to itself. So now the side triangle congruence theorem tells us that these two triangles, the one here, that is BCD, is going to be congruent to, well, let's do it this way, ABD, and then we got the same order. It needs to be CDB. Right, that's what I've said here. So that proves part J. Now, by definition, corresponding parts of congruent triangles are congruent by the definition of congruent triangles. We've got a pair of opposite interior angles, angle D and angle A. So DAB is congruent to BCA. So now what have we done? We've proved that both pair of opposite angles are congruent. That's part F. Furthermore, we also see that angle ABD, yeah, this blue one here is or purple, whatever that color is congruent to the blue one up here. Okay. Now let's see. Now back in the first paragraph, we had some congruent angles, particularly BAC and DCA. Let's find that one. BAC, that's the smaller angle right here. BAC and DCA, that's up here. Now look at that. if you think of this as a transversal here to these lines here, those angles are congruent. Oh, that's a pair of opposite interior angles, alternate interior angles. Okay, if you got alternate interior angles that are congruent in Euclidean geometry, well, and in hyperbolic geometry, but not spherical, that's enough to make the green sides A, B, and CD congruent to each other. And you have a Z going the other way as well. We already proved earlier that angle CDB was congruent to ABD, these two blue ones here. So that gives us another Z. All right, so where's our Z this time? It's the standard way, zip, zip, zip. And so that makes the top and bottom parallel. The other one that we had was over here, so that made the two blue sides parallel. So either way we go, we do the Z property twice, and we get some parallel sides on both sides. That makes it a parallelogram. Of course, there are no parallelograms in spherical geometry, so that doesn't apply. Now, let's look at what we have now. We have consecutive interior angles here are supplementary. Since these are parallel now, we've got their parallel, so consecutive angles are supplementary this way because these two are, the green ones are parallel, top and bottom. Makes the big angle at B and the big angle at C supplementary. And because the blue ones are parallel, we got a C going this way. The big angle at D, so that's CDA, is and the angle at C, DCB, that angle, those angles are supplementary. That doesn't work in the other two geometries. Okay, so in Euclidean geometry, well, in all three geometries, what do we have? We have opposite angles are congruent, and the supplementary part for consecutive angles is for Euclidean only. Anyway, we proved part E for Euclidean only. Now let's turn our attention to these smaller triangles here. Okay, just to pull the picture down so we can see it. Here's our smaller triangles. We're talking about like CXB and DXA, and then also the one down here, BXA and CXD. Okay, so let's look at the ones that have the blue sides there. Okay, so remember we've already established some angles, like we've got this angle at B, that angle DBA is congruent to CDB, the two blue angles. We've also got the two red angles were congruent. And then we got this vertical angles, the green ones. So really we have all three of the angles we've shown that are congruent. Even without the triangle angle sum theorem, we have that. And so what does that mean? Well, we also have these blue sides are congruent. We already proved that part. So that by either angle, angle, side, or angle, side, angle, angle, side, angle works in all three geometries. So that's enough to show that these two smaller triangles are congruent, and that's for all three geometries. And the exactly same argument applies to the triangle here, CDX versus ABX. Those are both congruent. Okay, so that proves part I. And corresponding parts of congruent triangles are congruent, so we have all the corresponding parts. Let's say CX and AX are congruent. That means X is the midpoint of side AC, and BX and DX are congruent. That makes X the midpoint of side BA. So we just proved that the diagonals bisect each other. That proves part G. So since the diagonals bisect each other, we see that a rotation of pi about the intersection of the diagonals will map A to C, C to A, D to B, and B to D. And so it has rotational symmetry about X by through an angle of pi. So we proved H. So now we've done it. We've done half of it at least. We proved that if we start with two congruent triangles, ABC and CDA, making a quadrilateral on the outside there, then each of those parts B through J are true. So let's just review. So we've proved that if triangle ABC is congruent to triangle CDA, we got a quadrilateral ABCD, then both pair of opposite sides are parallel, so it's a parallelogram. One pair of opposite sides are parallel and congruent. Two pair of opposite sides are congruent. Each pair of consecutive angles are supplementary. Two pair of opposite angles are congruent. The diagonals bisect each other. We have rotational symmetry about the intersection of the diagonals through an angle of pi. We have two pair of little triangles here when we take the diagonals, both diagonals in there. Triangle AXB is congruent to triangle CXD. Triangle AXD is congruent to triangle CXB. And then if we look at the other diagonal, forget the first diagonal, we get triangle ABD is congruent to triangle CDB. These are all true in Euclidean geometry, and most of them are true in the other geometries as well, just a couple exceptions. Now, let's go backwards. Let's show, so we proved all the properties of parallelograms right there. So now let's go backwards, okay, because if it's a parallelogram, it has this, and then it has all these other properties, okay? So now let's see if we can go and prove the converses, that if it is a parallelogram, it has these two congruent triangles, and then it has everything else. Or if it has this condition, then it's got these congruent triangles, and then it has all of these conditions, and so forth. Okay? So we got to prove that each one of these, B, C, D, E, through J, each implies A. Okay? Let me just pull this down here for reference. Okay, so we just need to show that each one of them applies J. So D implies A. Okay, so D was given a quadrilateral ABCD with both pair of opposite sides congruent. So we have opposite sides congruent. Take either one of the diagonals alone. You've got enough to use side, 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 and prove that D implies A. That works in Euclidean, hyperbolic, and spherical geometry. Since the labeling is arbitrary, we see that the proof of A implies J also shows that J implies A. If either diagonal divides the triangle in two triangles which are congruent with a rotation, then the other diagonal also divides the triangle in two triangles which are congruent with the rotation. And that's true in Euclidean, hyperbolic, and spherical. All right, now how about this one? What if we start with G? Given a quadrilateral ABCD with diagonals which bisect each other, how do you show that's a parallelogram? Well, let X be the point of intersection, okay? And we have AX, let's see here. AX is the same length as CX, DX, and BX are the same length. And the vertical angles are congruent, the green angles here. Well, that's enough to make these congruent by the side angle side postulate. And that means opposite sides are congruent for one thing. Okay. And if we have both, well, it works for this pair of opposite sides. Okay. And the same argument makes these two triangles congruent, because you have vertical angles, not the ones that are marked, but these vertical angles here, CXD and AXB are congruent. And since we have the side DX and BX are congruent, and AX and CX are congruent, we got side angle side makes these two triangles congruent, one at the top and bottom. So that means the corresponding parts are congruent. So now what do we have? We have both opposite sides are congruent, which is part I. So G implies I. Now once we have both pair of opposite sides congruent, erase one of these diagonals and just keep one, we've got two congruent triangles, which gets us to where we need to be. Okay. So if we either get G or I given, then A is true. And that worked for all three geometries. All right, what about this next one? What about H? What was condition H? It says we're given a quadrilateral with rotational symmetry about the intersection of the diagonals through an angle of pi. We see the rotation maps A to C. So rotation is going to do what? It's going to map A to C, C to A, D to B, and B to A. Since if that's a midpoint, well, let's see, we need to show that. Okay. All right, so what do we need? We need rotating this 180 degrees around. Okay, so think about what it means to have rotational symmetry. That means when you rotate it 180 degrees about this point, it is back where it started. When we rotate this A 180 degrees, it has to be somewhere on the line AC. Okay, and the only place on there that would actually still be on the original function is C. So A has to go to C, and similarly C has to go to A. And the same argument holds for the other lines, the other endpoints. D has to go to B and B has to go to D. Well, that means that the entire triangles are going to be rotated that way, and so they're going to be congruent to each other. Or we could do it by knowing that the rotation maps the congruent side to congruent side. Okay, so far we've established that any one of D, G, H, I, or J imply A in Euclidean, hyperbolic, and spherical geometry. So those are the ones that work in both directions. Now, let's see here. How about B implying A? What if we just start with knowing it's a parallelogram? That's the sort of the more typical way we looked at it in the last video, is we just started assuming it's a parallelogram. So we know we have opposite sides parallel. Now, first of all, that doesn't even possible in spherical geometry. In hyperbolic geometry, that doesn't necessarily tell us a lot because there are so many different parallels. So this part's only going to be for Euclidean geometry. All right, but if we have parallel sides here, we can use the Z property. See that? And so that's going to make these blue angles congruent. And we got a Z going this way with parallel lines. So the angle DAC and the angle BCA are congruent. So that's alternate interior angles when you have formed by transversal to parallel lines must be congruent, the Z property. And in this direction, the Z property works in Euclidean geometry, but it doesn't work in hyperbolic. Okay, so now we have some angles that are congruent. And then what else do we have? So then we have, oh yeah, the diagonal is congruent to itself. So AC is congruent to itself. So now we have enough to do angle, side angle. The angle, side angle congruence theorem tells us that B implies A. Remember, A is that we have two congruent triangles. So if it's a parallelogram, it does make it into two congruent triangles. C implies A. If we're given quadrilateral with one pair of parallel sides and a diagonal that are okay, or one pair of sides that are parallel and congruent. So let's see, what do we do? It's which side did I say? I said A, B, and C, D. All right, that's the green ones. The bottom here and the top, if we assume they're both parallel and congruent. Well, once again, since these are parallel, we got our Z going. See, what we were trying to show that ABC is congruent to CDA, right? So we're using the orange diagonal. We're not using the other one. So we have this side right here is parallel to the one up here. And we got the orange diagonal. So there's our Z, kind of upside down Z or backward Z. But angle BAC is congruent to angle DCA. They're alternate interior angles when you cut a transversal CA, cutting these parallel lines here. Well, we also have these sides are congruent. So, and then of course we have this diagonals congruent to itself. So now we have enough for side angle side postulate, and that's going to make the two triangles congruent, which is what we were trying to show. But we did use the Z property in the direction that's only true in Euclidean geometry. Okay, what's next? E implies A. So what's E? E says if we're given quadrilateral ABCD with each pair of consecutive angles supplementary, okay, which by the way is only even possible in Euclidean geometry, then that's enough to make everything parallel. So the fact that this one doesn't have any diagonals in this one, if you have ABC and BCA, the big interior angles at B and C are supplementary. That makes the top and bottom, the green ones, parallel by the C property. And similarly, if BC and A, angle B and angle A, that is CBA and DAB, are supplementary, that's going to make the C property is going to make the blue ones parallel. So that's going to make it a parallelogram. And of course, once we already showed that a parallelogram applies, we get the two congruent triangles. All right, let's see what we've got here. We're almost done. F implies A. See, what was F? We're given a quadrilateral ABCD with both pair of opposite angles congruent. Okay, so now no diagonals necessarily, but the big angles here and here, here and here are congruent. Now, if we look at Euclidean geometry, the sum of the measures of the interior angles is 2 pi. So we have 2 pi as the measure of A plus measure C plus measure B plus D. But A and C have the same measure, so you can replace measure of angle C with measure of angle A. So you got 2 at measure A, and measure D and B have the same measure, so you can replace that measure of D with that measure of B. So we got the 2 pi is 2 measure A plus 2 measure B. Divide both sides by 2, and we get pi as measure A plus measure B. They're supplementary, and by the C property, that gives you a parallel. Okay, and we'll see that for both sides. So that makes it a parallelogram in Euclidean geometry. So, at least in Euclidean geometry, we've shown that any one of the conditions B, C, D, E, or F implies conditions A, and I've given you the exceptions of when it doesn't work in the other geometries as well. So, each one of these conditions here in our table that we started with is equivalent to it being a parallelogram, right? And we all were proved by going by way of eventually showing we had some congruent triangles. So all of these, along with this one over here, are actually equivalent conditions. They're minimal conditions for having a parallelogram. Now, the ones that don't work, remember there are no parallel sides in geometry that's spherical, and for hyperbolic geometry, we should be able to find some parallelograms where some of this stuff doesn't work. You can actually look at the examples that I looked at in the previous video to see some hyperbolic parallelograms where some of these things don't work. Notice that the key for going from any of the properties on the right column to going to any of the other properties in the right column is to go by way of establishing that we have this pair of congruent triangles via rotation. Triangle ABC is congruent to triangle CDA. When you're writing out these proofs, establishing this pair of congruent triangles, is the key step. Okay, somewhere in the middle of the proof. One of the most central basic things that high school and college geometry students should be able to do is write out good proof about parallelograms, right? Any competent high school or geometry or college geometry student, okay, should be able to complete the following tasks. The proof that I did actually includes a proof of all these, but you should be able to take each one of these and without relying on any of the other properties of parallelograms, write out a good little proof of this. It won't be as complicated as what I just did because there won't be as many moving parts. It'll be like one little piece of what we did earlier. So you should be able to, for example, take, given a parallelogram, prove that the sides of the parallelogram in either diagonal forms a pair of congruent triangles. Or take a quadrilateral as a parallelogram if and only if it has two pairs of opposite congruent side. A quadrilateral is a parallelogram if and only if it has a pair of sides that are congruent and parallel. A quadrilateral is a parallelogram if and only if its diagonals bisect each other. A quadrilateral is a parallelogram if and only if it has two pairs of opposite congruent interior angles. So at least in Euclidean geometry, you should be able to take any one of those and write down a really good proof of that. So I challenge you to go ahead and write out proofs of all of those. If you're in my class, I would expect you to do those, be able to do those kinds of things on exams, hopefully perfectly. So then the next question is, which of these statements is true in hyperbolic geometry, and how about spherical geometry? And we'll let you think about that. If quadrilateral ABCD has triangle ABC congruent to triangle CDA, remember the order matters, then it is a parallelogram in Euclidean and hyperbolic geometries, and in spherical and hyperbolic geometries it has almost all the properties of a Euclidean parallelogram. However, parallelograms do not exist in spherical geometry, and there are many more parallelograms in hyperbolic geometry that do not have either the two congruent triangles or the various properties stemming from them. The difference in the geometries results from the differences in properties of parallel lines. Because the Z and C properties only work in one direction for hyperbolic geometry, many of the implications above only work in one direction. Remember that trapezoids and parallelograms do not exist in spherical geometry, but the classic quadrilaterals ABCD with triangle ABC congruent to triangle CDA does exist. In hyperbolic geometry, the classic quadrilaterals quad ABCD with triangle ABC congruent to triangle CDA, in other words, quadrilaterals with rotational symmetry, is a subset of the larger class of all parallelograms. That's in hyperbolic geometry. However, in Euclidean geometry, the class of quadrilaterals, quad ABCD with triangle ABC congruent to triangle CDA, that's the ones with symmetry, rotational symmetry, turns out that is exactly the same as the class of parallelograms. And there are many different minimal sets of conditions that can guarantee we're in the class of parallelograms in Euclidean geometry. And there is a look at the GeoGebra thing that I have. Here it is. Here's, so you click on classified by numbers of parallel sides, click on parallelogram. You can see the angles measured. We see the diagonal. You can say there are other diagonal. You can turn them on or off. We can see it's interior shaded and figured out the area. And we can list, there's the interior of it, and right there's the value for its area. And we can list out properties. All right, and these are the same things that we were just talking about. So we have proved the parallelogram theorem. We know all about the properties of parallelograms, and we know if we can make true converses of these properties as well.